Imagine if every molecule left a fingerprint. Infrared spectra do exactly that. In the next few minutes, you learn how to read those fingerprints and quickly identify the most common functional groups with confidence. We'll start by breaking down the axis, then map the key functional group regions, and finish with 2 fast examples you can practice on. Infrared light makes bonds vibrate. The horizontal axis is wavenumber in inverse centimeters, which tracks vibration frequency. The vertical axis is percent transmittance. A deep dip means the sample absorbed that light strongly, so that vibration is present. Different bonds vibrate at different spots. Single carbon-hydrogen bond stretches sit just below 3,000 inverse centimeters. A double carbon-hydrogen bond of alkenes stretches just above 3,000 inverse centimeters. A carbon-hydrogen triple bond, like in a terminal alkyne, sits near 3,300 inverse centimeters and is sharp. Here is a fast mental map you can rely on. OH is a broad hill from about 3,200 to 3,600 inverse centimeters. NH is sharper and less intense in the same neighborhood. Carbon triple bonds live a bit above 2,000. Carbonyls give a tall, narrow peak around 1,700. Aromatic ring stretches gather near 1,500. The dense fingerprint region below 1,400 helps confirm details. Let's practice. In spectrum A, there is a broad, rounded band from 3,200 to 3,600. That is classic OH. We also see saturated carbon-hydrogen below 3,000 and no strong peak around 1,700, so no carbonyl group. Below this, sharp absorption near 1,100 is labeled C single bond O stretch, a defining feature of alcohols. Now, the quiz answer. This IR spectrum belongs to an alcohol. A common mix-up is OH bond versus NH bond. OH bond is broad and rounded because hydrogen bonding smears out the signal. NH bond is sharper and usually less intense, sometimes showing a pair of small spikes for a primary amine. Now, here is a quick checkpoint. If you can name where the OH bond lives and where the carbonyl bond lives, you are already reading most spectra faster. Want to lock this in? Your personalized practice test and flashcard set are all waiting for you. Tap the link and give yourself a quick check. Next, use a variation. A terminal alkyne often shows 2 clues: a sharp sp carbon hydrogen near 3,300 and a weak carbon triple bond near 2,200. An internal alkyne lacks the sp carbon hydrogen, so that 3,300 spike disappears. Now let's combine multiple clues at once. First, a tall, narrow carbonyl bond near 1,710. Next, sp2 carbon hydrogen just above 3,000 tells us there is unsaturation. Then the cluster near 1,500 points to an aromatic ring. Out-of-plane bends between 650 and 900 help with substitution patterns. Put that together, and an aromatic ketone is a good call. One last tip, watch for shifts. Conjugation next to a carbonyl lowers the frequency a little, so a conjugated carbonyl group can slide down toward 1,680 to 1,700. Do not mislabel it as something else just because it moved. Here is a repeatable 3-step scan. Step 1. Scan for the big flags: OH, NH, or a carbonyl bond. Step 2. Check the carbon-hydrogen zone to tell saturated from unsaturated. Step 3. Look for extras like triple bonds, aromatic patterns, and then use the fingerprint region for confirmation. To recap, you saw how the axes work. You memorized a few signature regions, and you used a 3-step scan to identify alcohols, alkynes, and carbonyls. With practice, these peaks will jump out at you. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.